things which may be of interest to look at for younger researchers. I select to call my topic fundamental Troika, and I hope that by the end of the talk you will learn what Troika is and why I think it's rather fundamental. So let's start from very elementary and well-known stuff. So if we are taking two-sided cone, so I did not draw full other half of the cone, but indicated its presence here. Then we may intersect it with planes in different ways. So this is something which already was known for a couple of thousand years, starting from ancient Greeks. Archimedes and Euclides already did some mathematics related to conic section. And basic facts, which already was discovered at this time, what essentially you get three different type of sections. So in the elementary case, when plane is perpendicular to the axis of the cone, you get a circle, or if there is some inclination here, some angle, it will become an ellipse. Then if a plane is parallel to the one of the generators of cones, you will get a parabola. And when there is a situation where there is hyperbola, for example, if the plane parallel to the axis of the cone. All three types of conic sections appear from the same source, from the same cone, but they have some properties which distinguish them among themselves. In particular, there are always property which is particularly possessed by only one type of section. For example, elliptic section is compact, while parabolic and hyperbolic are unbounded. Hyperbolic section has two branches. So second branch shall present here upward half of the cone. I did not draw it, but it's easy to imagine. While all other conic sections, elliptic and parabolic, just consist single branch. We are connected. And distinguished property of the parabolic section, what it's fragile. So you need exactly have a plane parallel to one of the generators. Small deviation in either side will transform your section either to elliptic or to hyperbolic. So while two other sections a bit of stable, so you may slightly change the angle and type of the section remains the same. In the Wikipedia page about conic sections, there is some other mathematical objects which seems to be following the same classification. This is quadratic form, curvature, second order pseudo-differential equations, and Moebius transformations. So this is what Wikipedia lists as other objects related to that separation in three types of construction. So let us look on them one by one. So starting from quadratic form, this is rather general quadratic form here. By changing coordinates or changing variables, we may transform it to one of the canonical expression. So it's reasonable to consider, along with the quadratic form, associated quadratic equation, just putting y equal to 1, sorry, and usual discriminant of this quadratic equation when determine the type of the section or the form which we obtain. So it can be two squares both with positive sign, it may be squares with opposite sign, or one square may disappear, so if it's a parabolic situation. So again, there is a sharp value for the parabolic case, it shall be exactly 0 for discriminant, and two other cases are more flexible, so it's just a sign, not particular value. And there is again known properties for corresponding quadratic equations. What discriminant negative means there is no real roots, single root for the boundary case, parabolic case, and hyperbolic situation have two roots. Form is positive definite in elliptic situation and parabolic situation, but indefinite may take both positive and negative values in hyperbolic case. So again, parabolic case is different because it degenerate. There is no dependence from y in new coordinates here. And we see what this property distinguish different cases here. Important observation related to divisors of zeros. Well, actually, for rigorous definition of divisor of zero, we usually exclude zero itself, but for our purposes, it may be worth to consider it as a particular case of divisor of zero. So in elliptic case, there is just one zero itself. In the parabolic case, we have the entire, well, it's in this moment not exactly divisors of zeros which I'm speaking about. This is about where the form take value equal to 0 itself. So it's just one point on the plane. It's vertical line in the parabolic case, or what in physics called light cone. And this is two crossed lines, x equal y or x equal minus y in hyperbolic case. So with red objects, we will meet several times in this talk later. And this picture will be reproduced just to have a reminder about them. About second order PDEs, so here algebraically they are rather similar to quadratic forms. So just instead of squares, which we have here for variables, we have the respective powers of derivatives. So elliptic equation is just the sum of second order derivative of function of two variables, whereas hyperbolic equation with the difference. And for parabolic case, we rather put the first order derivative to avoid a full degeneracy of this equation. So this is Laplace, Heat, or diffusion equation, and also wave equation. I draw here the solution of initial value problem. We treat y as a time parameter, so there is space parameter x, there is certain value, initial value for x, the same in all three cases, and when along the time y, it's evolved in particular way. So maybe it's elliptic and parabolic case make a good pick for the typical exercise, find 5 or 10 distinction between pictures. Really we can spot something. So for example, this edge which is closest to us is more curved in the parabolic case, more flat in elliptic, but we may see a sharper shadow in elliptic case rather than in parabolic. This is just because in parabolic case heat diffusion just decay more faster, so there is no it's really sharply drop here in this area. It's much more easy to spot the difference for the wave equation. So I draw here the solution in the form where one pike is just generate a wave traveling in positive direction, and another spike generate a wave traveling in negative direction. So they go one across to another, so meeting in the middle. So actually, if you look on the edges of these waves, which are traveling here in space-time, you will see what they are crossing again along the corresponding like cone in the middle point. So just to give a little bit more illustration for difference of these initial value problems, I animated. So the same initial value here propagate in blue color as a wave. So we have two waves passing in opposite directions, one through another, completely preserving their initial shape. And green and red are correspondingly parabolic and elliptic situations. So parabolic more curved a little bit, but again, they start from the same value. We see what green one parabolic is decaying faster, especially in where it was sharp spike, and there are some distinctions. So we see what behavior of initial value solution is different in these cases. So again, at the moment, I am just giving that brief summary overview of topics mentioned in the connection to the division on elliptic, parabolic, and hyperbolic cases in different areas. And then we will just go in a little bit more careful detail. So nothing particularly here need to be memorized about that animation. So we move further. Next mentioned object is a curve, Gaussian curve, curvature, sorry, which we have again in the split into three. The Gaussian curve is defined in the following way. We take a curvature of two main curvatures on the surface and multiply them. So for spheres, they are both positive. For hyperboloid, it's one positive, another curvature is negative, so product is negative. And for cylinder, one curvature is equal to 0. We have straight line here, so product will be 0 as well. So we may think again about continuous transition between them. So if we take the sphere and start make it wider in one direction, so it became instead of sphere some ellipsoid. And if we go further and stretch it to infinity, that wide ellipsoid eventually became the cylinder. And then if we will continue moving from a circle to straight line, so next step shall include that negative direction here. Negative curvature, so product will be negative. So there is like a continuous parameter here, which can be introduced into that picture. And again, parabolic case is just some boundary value, sharp boundary value, which separate two positive and negative situations. last object mentioned on the Wikipedia page is Moebius transformation. So Moebius transformations are given as fraction linear formula. We initially think it just as transformation defined on the real line from reals to reals. And one of the characteristic properties of these transformations is presence of fixed point. To have a equation for the fixed point, generate a quadratic equation, and this quadratic equation may have no solution. So this is blue is the graph of corresponding Moebius transformation, and for fixed point it shall intersect with green line, of course. It may be touching with green line in one point, double root, and it can be hyperbolic situation where we have two fixed points for this transformation. And a rather generic form of this Moebius transformation, which has this type of fixed point, are presented here. We will meet them again later when we will introduce a bit of justification here. So what we have so far? So general setting is look like this one. We have certain parameter, one real number, which goes like from minus infinity to plus infinity, and there is certain singular value, something which is separating two different areas. One of them can be associated with elliptic case, and another side of this parameter correspond to hyperbolic one. This is like a general reason why that separation appears. And there are a collection of objects which follow that general pattern. But it's a little bit fuzzy at the moment. There is no clear connection or something what we can carry out from one case to another, say from curvature to the differential equation or to quadratic form. So it's a little bit like in one area, good neighbors, but not relatives, let's say. I will try to add more link between this object, and the key point for it will be Moebius transformations, Moebius map. But before we will proceed with clarification, with additional connections, I propose to look on the following question. Assume we have two-dimensional vector space R2, and we want to upgrade that vector space to an commutative associative distributive algebra. Element of this two-dimensional vector space we may denote as U plus iota V. U and V real numbers. Iota is just keep as a separator between two components of the vectors, two real components. When if we building the algebra, when opening product of two such vectors by associativity, commutativity, distributivity lead to two natural terms where we have just product of real numbers. Here we have that iota times certain expression of real numbers. So there is no problem to understand it within our vector space. But also we will have iota times iota, iota squared. And to put it back to two-dimensional vector space, we need to assign a certain value from our vector space to iota squared. So let us say it will be some alpha plus iota b. what are possible options? Interesting situation is what I learned with case or that problem from a book not on algebra but about some mathematical models for hydrodynamics, so quite applied book. And the answer is as follow. So if we draw that alpha beta parameters plane, then there is a region where that value of this expression, which is kind of a determinant for in this case. If it's negative, then by a change of coordinates, we may reduce our algebra to very well-known complex numbers. And our iota is nothing else, just as imaginary unit, and I square is equal to -1. So that what can be achieved. But there are two other cases. One of them is what we have value of that discriminant equal to 0. When I denote corresponding iota as particular situation as epsilon, something we may think so small, what its square is exactly 0, so negligible what it's 0. Important thing what squaring to -1, you cannot use real numbers. It's something imaginary, as we said, need to be introduced. But to get a square equal to 0, you can use 0 itself, of course. So, but what we are asking, what it shall not be a real number, because otherwise our two-dimensional vector will collapse just to real numbers, not to a vector. So it's something different from 0, something which square it to 0, but not 0 itself. So that imaginary kind of unreal number. And similarly, there is hyperbolic situation where we have that iota squared to 1. Again, it's not +1, it's not -1, otherwise we will have a real number here. So it's something else which square it to 1, something non-real. Well, it may be for many of you who see the dual and double number first time, I'm just making that assumption because I learned about their existence when I was 40. And for 20 years, I was familiar with quaternions, with Clifford algebras. I know what where exist, what were useful, but such simple objects as dual numbers and double numbers somehow did not pass across me earlier. Why this happened? Very simple reason, because complex numbers really needed to solve quadratic equations. So you cannot solve quadratic equations in general if you don't have something which squares to -1. Complex numbers are algebraically closed. So if you have equation with complex coefficient, solution will be again complex numbers. You don't need to introduce anything else. And there is no zero divisors again except 0 itself. So this is that picture you may see which already appeared before. Parabolic and hyperbolic case, dual and double numbers miss all that good properties. They are not algebraically closed. You may again have equation with this dual or double number coefficient, and you cannot solve it. You need still complex numbers. There are plenty of zero divisors. Everything times that epsilon with any real numbers, square it to 0, of course. So it's zero divisor. If we have 1 plus j, we multiply it by 1 minus j, it will be 0 as well. So we have this light cone built out of zero divisors for double numbers. So dual and double numbers seems to be not useful because not algebraically closed, not needed because we can solve with simple equation with reals, and they seems to be troublemakers through their zero divisors. So plenty of reasons not to deal with them. Nevertheless, we will see what they repeatedly appear and turn to be helpful in quite a lot of situations. To explain where this number appears, we consider group SL2R. This is group of 2 times 2 matrices with real entries and determinant equal to 1. So because group operation is matrix multiplication, product of 2 such matrices again has determinant equal to 1. And if determinant equal to 1, it's non-zero, so matrix is invertible. So such matrices do form a group. Standard mathematical way to study an object is to study its building blocks. For a group, it will be subgroups. What are subgroups of SL2R? For two-dimensional case, it's what's called affine group or IX plus B group. This is presented by this upper triangular or lower triangular matrices. So again, by matrix multiplication, if you multiply two upper triangular matrices, you will get again upper triangular matrices. This is one subgroup. It will not be so central to our study, but we are more interested in with three cases, again three cases of one-dimensional subgroup. So this is a Lie group. For this reason, there is corresponding Lie algebra, and element of this subgroup can be obtained by exponentiation of certain element from Lie algebra. Lie algebra consists of matrices with zero trace. So subgroup A and K will appear in our situation, very important. And it's possible to demonstrate what all one-dimensional continuous subgroup of SL2R are similar to one of these groups. Again, we may immediately notice what groups are rather different. For example, K subgroup is compact. So this is why it's called K. We have here periodic function cosine and sine. So parameter here is just limited to unit circle value, so minus pi pi. And we just outline how subgroup, one-dimensional subgroup can be parameterized through this exponentiation from Lie algebra. We define exponent by Taylor expansion, Taylor series for exponent function, and because we have matrices, we just can calculate their corresponding powers and build such an expansion. So for the classification of one parameter subgroup is important or enough to classify just the with 2 times 2 traceless matrices. And what are options for 2 times 2 traceless matrices? So this is a lemma which just describe what is the square. So traceless matrix has this form when we have A minus A on the diagonal. And square of such matrices, and it's easy exercise, this is identity matrices times certain value. This value is again like the discriminant of a quadratic equation, so have a similar form. And if we square, so we correspondingly get identity matrix times a certain value. So that X 2 times 2 matrix behave very much like one of the this hypercomplex unit I, epsilon, or j, which we had seen before. So what exactly correspondence here? So value of why first of all this lemma produce classification, just because if square is identity, that means what cube will be just x times a factor. Fourth power will be again identity, and so forth. So Taylor series, which we discuss here, just split into sum of even and odd powers. All even powers are identity, our odd powers is just matrix X itself. So it's important just to have what time of series we have, and it's known what if we sum up even odd series of this type, we get either sine and cosine usual elliptic one, or hyperbolic sine and cosine if there is no alteration of signs, if that determinant is positive. If we have here x square identity matrix times 0, so that means Taylor expansion of exponent just terminates, and so we have lower triangular matrix here. So nothing so exciting happen, but that is important parabolic case. The generator of corresponding subgroup can be uniformly written just in this, you see, upper right corner, we put the corresponding square of the imaginary unit. And if we will calculate eigenvalues of this matrices, then again we come to quadratic equation in characteristic equation for matrix with no real roots for elliptic situation, one double root in the parabolic, and two distinct real roots for the hyperbolic situation. Eigenvalue of matrix X are related to the presence of fixed points for these subgroups. So if there is no eigenvalues, there is no fixed point. If there is one eigenvalue, there is one fixed point for corresponding Moebius map, and similarly for hyperbolic one. So this is how it's happened. Why we are speaking about Moebius transformation, or why I spoke about Moebius transformation in previous slides. So just because this is the action of the SL2R on corresponding homogeneous spaces. So just let me again briefly recall elementary algebra. If we have a group, we can introduce the equivalence relation group and subgroup H, when we can introduce an equivalence relation saying what two elements of the group are equivalent if they are different by right multiplication element from the subgroup. Then if we consider such equivalence relation, there are corresponding equivalence classes, and if we multiply elements of the group from the left, then of course equivalence classes defined through the right multiplication will be preserved. So action of the group on itself by left multiplication respect that equivalence relation, so it's factor through the action on corresponding homogeneous space. So in this way, what we can take, we take element of from homogeneous space, find its representative, multiply by G on the left, we get element of on our group, and we pick up just equivalence class which contain that new element, so that we became the multiplication on or action of the group on corresponding homogeneous space. If we take SL2R and subgroup F being that affine group X plus B group, two-dimensional one, then homogeneous space can be parameterized just by that fraction b over d, and just simple computation shows what with parameterization action of SL to R on the that real number is reduced to Moebius transformation. So fractional linear transformation appear here on the real line. So we will work with this thing. So it just model simple situation with two-dimensional subgroup. Things became more interesting if we will go to one-dimensional subgroup. In this case, group SL2I itself is three-dimensional. We factor out one parameter by equivalence relation on the one-dimensional subgroup. So remaining homogeneous space is parameterized by two numbers, two real numbers. So we have upper triangular matrix and two real numbers U and V just describe equivalence class. So if we will repeat that algebraic computation, we come out what depending of which subgroup we are taking, A and K, we will get formula of this type, which does not look very attractive itself if we will stay with two real numbers U and V, but it's again transformed to the fractional linear transformation if we will use this three type of hypercomplex numbers which we mentioned before. Complex numbers for subgroup K, dual numbers for subgroup N, and double numbers for subgroup A. So uniformly action of SL to R can be written on its homogeneous space using this three type of different numbers. So this is the point which I promised you, where double and dual numbers appear very naturally, and actually attempt to avoid them will be rather inconvenient. So this is a situation where they're really helpful, despite of their clear disadvantages compared to just complex numbers. Let us visualize a little bit with algebras which we had before. So in general, element of SL2R, 2 times 2 matrix, can be decomposed into product of three matrices from subgroup A, N, and K. So that is known as Iwasawa decomposition. So we have this diagonal matrix, we have this upper triangular matrix, and we have this compact matrix from subgroup K. So easier to start from diagonal and upper triangular matrix, but if so, and we are working in all three situations. So here there is that iota, which may be any of three possibilities which we discussed before. If we have upper triangular matrix, then we have here 1, V, 0, 1. There is no product of iota to itself. No, there is no iota squared. So it doesn't matter what is value of iota squared for this action. So I started from the A. Similarly for the diagonal matrix, if we have tau here, 0, 0, tau, again, it's just a real computation, computation with real numbers, so no iota squared. Action of diagonal matrix is just scaling. So orbits are shown as with rays. There is here gray arrows which demonstrate how orbits are moving. Similarly, for upper triangular matrix, we have shifts. Real component, first component is transformed, but second component, vertical component, is unchanged if we have this matrix. So these two matrices act in rather straightforward way, and it does not feel any difference of the type of number which we are using. What happened with the third matrix compact subgroup K if we apply it in free situation? First one with complex numbers, it's rather well known. It will be hyperbolic, what called hyperbolic rotation on the Lobachevsky half plane. So it's non-Euclidean geometry here. So straight lines are given by these arcs orthogonal to the real line. And we have this type of rotation. Gray arrows shows how orbits are generated. We have rotation with the center in the imaginary unit. So we treat horizontal direction as real and vertical as imaginary. If we will apply the same transformation but to dual numbers, orbit will become parabolas. So just in the same way as we get circles before. And if we apply it to double numbers, you will probably at this point shall not be surprised what orbit became hyperbolas. So we have three conic sections appeared as orbits for subgroup K in Moebius transformation, fractional linear transformation. By the way, if we will look on the corresponding gray arrows, that vector fields which are created by this subgroup K, they again have that uniform expression depending on parameter sigma. Sigma is the value of iota squared. It's plus minus 1 or 0 for corresponding type of numbers. So there is uniformity, certain uniformity if we use iota, if we use sigma, which is square of iota. So we may consider all three cases at the same time. Moreover, connection is very closed, and it's bring us back to the first illustration on this talk. That previous three type of orbits, it's not just shapes of conic section. It's really conic section, and the same value of parameter t produced the respective point on the same generator of the cone. So actually, action of subgroup K is produced by rotation of this cone around its axis. So conic section is not just by formula, but also by its geometrical origin, which appears here. Similarly, if we ask what are fixed points, we already seen rotation in the Lobachevsky upper half plane, which are around the imaginary unit I with subgroup K. If we will ask which Moebius transformation in dual numbers fix epsilon, it will be subgroup n prime, lower triangular matrices, and orbits will be with orbits. And it's fixed not only epsilon, but entire line. So all zero divisors associated with the dual numbers. And if we will look on the double numbers and ask which subgroup, which transformation fixed J, then we will discover that hyperbolic type of rotation with hyperbolic cosine and sine function here, and it fixed not only J itself here, but light cone passing point J. So if J is fixed, light cone is kind of invariant object, special object, which will be fixed as well. So we already obtained conic sections from the Moebius transformation. Now we come to the curvature. curvature connected to Moebius transformation as well. It's connected in the following consideration. We defined, or we considering fractional linear transformation. We divide by some numbers, but we cannot divide by anything. For complex numbers, we cannot divide by zero. Denominator in fraction is equal to zero, division is not possible. To have a bijection as Moebius transformation as bijection, we need for that special denominator assign extra point, and this is the reason why we oftenly consider Riemann sphere as a compactified version of the complex plane. So, and typically they are connected by polar projection. So from the North Pole, we project a sphere to the plane. So when Moebius transformation on the plane are related to some conformal mapping of the sphere. This is for complex numbers. It's quite well known and appear in many courses, undergraduate courses. What happened with dual numbers? With dual numbers, there are much larger set of exclusion from division. We cannot divide by anything which contain lambda epsilon, so entire line. So we need more exceptional points. To have a kind of compactification, instead of Riemann sphere, we need to take something like cylinder. When that exceptional line does not have images on the plane, this is additional object which added, a collection of additional points added if we compactify the plane, if we make fractional linear transformation everywhere defined as bijection. What happened with double numbers? With double numbers, divisors are forming light cone. So we have this natural compactified object as hyperboloid. So here with red lines does parallel to the yellow plane, they does not have corresponding polar projections, and so they are new ideal objects added to our plane. So compactification requires shape like that. So as you see, these three types of Gaussian curvature objects appears very naturally again in respect to Moebius transformation, just because we need resolve certain algebraic properties related to the division of corresponding numbers. What about second order partial differential equations which we have considered? What their connection to Moebius transformation? Connection is very straightforward. If we make corresponding fractional linear transformation in complex dual or double numbers, that will be the symmetry of the equation. So we take, well, there are some technicalities of how to do it properly, but generally correspondence is like that. So if we have Laplace heat and wave equation, do fractional linear transformation in complex dual and double numbers, and solution will be transformed to the solution. So that is important connection. But complex dual and double numbers has much more wider roots in physics. For complex numbers, this is not a secret, of course. We have Euler formula, which express exponent with complex power through the cosine and sine. This is canonical periodic oscillating function. So whenever you have something periodic oscillating, complex numbers are helpful. And when we consider quantum mechanics, which is also known as wave mechanics, then appearance of complex numbers is just a need. So it's not non-commutativity of observables, which is crucial for quantum mechanics. It's really usage of complex numbers, which is needed. So I have discussed it in some paper, but it's probably better not to go into details in this talk. When dual numbers are useful to describe classical relativity, so-called Galilean relativity of classical mechanics. So there is a nice book of Yaglom which describe geometry with the dual numbers and corresponding physical applications in details. So it's just best to look in this book for the description. Finally, double numbers with this light cone, which appears as divisors of zeros. This is perfect model for Minkowski spacetime and corresponding relativity, which described by Minkowski spacetime. Again, there are good books which in details describe that connection between algebra and physical models. So probably I will just pass through at this point. Here is the summary table. So initially we have this cloud of objects, as I said, are good neighbors, but maybe not relatives. And we finally discovered what all of them are related to Moebius maps. So if we are taking two-dimensional algebras, then they help us to describe fractional linear transformation as action of SL to R in natural way. Conic sections, they appeared as the orbits of corresponding actions. And from orbits, it's easy to demonstrate if they are orbits, they form invariant family of curves. So for geometry in complex numbers, invariant family are circles. For fractional linear transformation in dual numbers, invariant family are parabolas. And for double numbers, invariant family formed by the hyperbolas. Quadratic forms are naturally classified through the using of this iota, which may be squared to -1, 0, or 1. Curvature of geometrical objects appears if we consider bijections and compactify the corresponding homogeneous spaces. And SL2R derive asymmetries of corresponding to second-order partial differential equations, so naturally connected with physical problems which described by these equations of mathematical physics. Just to summarize what we find during this talk, what there is what I called similarity and correspondence. There is just a parallel employment of three subgroups K, N, and A, or where modification N prime, A prime, as we consider it here. So we may treat them at the same time using the same formula, same technique, if we are employing the corresponding hypercomplex number, complex, dual, and double. So without these numbers, or in general, it seems there are too much distinction, say, between compact group K and non-compact group A. But if we use the complex numbers, hypercomplex numbers, respective one, it's possible hide or overcome that distinction between different situation using the algebra related to these numbers. Finally, I promise you to tell what is Troika. Troika is this type of carriage with 3 horses in Russian. Of course, it's usually enough just 1 horse to drive a carriage, and maybe if a person is rich, I can use 2 horses at the same time for a carriage, but 3 horses give more fun, more enjoyment, and bigger speed in movements. So this is why I suggest to study elliptic, parabolic, and hyperbolic situation all at the same time, just using the proper technique which describe them. Here is a few papers and books which was mentioned in the talk, just in case you wish to look and see a little bit more on the discussed subject.